Good morning or good afternoon, everyone, and welcome to Genome Webinars. I'm Julia Caro, Managing Editor at Genomeweb, and I'll be your moderator today. The title of today's webinar is Strategies for Containing Cloud Computing Costs in Healthcare and Life Sciences Research. This webinar is sponsored by Secera Labs. Our speakers today are Michael Kroll, Director of Cloud Engineering at Gridstone Bio, and Dr. Phil Yules, founder of NF Core and lead developer advocate at Secera Labs. You may type in a question at any time during the webinar, which you can do through the Q&A panel, which appears on the right side of the webinar presentation. And we will ask our speakers your questions after their presentations have concluded. Also, if you look at the bottom tray of your window, you will see a series of widgets that can enhance your webinar experience. So with that, let me turn it over to Michael. Please go ahead.
Thanks, Julia. As Julia said, my name is Michael Kroll, and I'm the Director of Cloud Engineering at Gridstone Bio. I've been in the IT space for about 20 years, with the latter half being in the biotech space. Really excited to talk with you all today, and here's what I plan on covering. First, we'll do a talk about Gridstone, go over cloud costs, leveraging spot instances with AWS Batch, right-sizing of resources, and cutting compute time and cost with efficient storage usage. Before we get started, I want to give a little background on who Gridstone is. Gridstone Bio is a clinical stage oncology and infectious disease biopharma company taking immunotherapy to the next level. We're taking on cancer, we're tackling some of the world's most prominent infectious diseases, and we're doing it with our proprietary AI model, Gridstone Edge. So how does Gridstone use Nextflow on AWS? We leverage pCluster and AWS Batch. We maintain a stateful pCluster to give bioinformatics and scientists the stable environment they have come to know and expect while allowing cloud to reproduce the environment instantly through code. We use Apptainer and HPC, Docker and Batch. This allows us to get the HPC world the security it needs with Apptainer and single container image across both pCluster and Batch. We also leverage Open on Demand to provide RStudio, Jupyter Notebooks, and other scientific tools. Gridstone develops and maintains its own AWS Batch environments, as well as a custom in-house AWS Batch Nextflow launcher to leverage some of the tricks and tips we'll talk about today. This allows us to use the same methods from automated AWS Batch jobs from triggers like AWS Lambda and jobs launched from Nextflow Tower. We dynamically create an infrastructure configuration that is joined with the pipeline configuration on runtime. This allows the cloud team to maintain the environments across regions and AWS accounts easily, while reducing scientists' need to know the environment by providing things like email configurations, Docker registries, and a list of Nextflow process labels which dictate a batch queue with specific characteristics and more. To properly manage these environments so that they operate the highest efficiency and effectiveness, we need to control costs by leveraging spot instances, right-size our resources and processes, and use storage efficiently. Let's talk about cost. In order to control costs, you first need to know what you're working with. That's where tracking comes in. In order for us to control it, we need to track it. So Nextflow provides estimated compute costs on a per job basis. Keep in mind that this is only compute costs and does not include associated costs with EBS and S3. Use tagging on all your resources. By tagging your resources in a batch environment, you can use the native AWS Cost Explorer or third-party tools to track all costs relevant to batch. This will include the compute costs, EBS, and S3. By creating a batch environment per project, you can accurately track costs on a per project basis. Once you have visibility into your costs, then you can start finding ways to reduce them. Here are some general recommendations. Use public subnets to avoid any NAT gateway charges, but also remember to check your security groups to not leave any open ports. When using private subnets, which is what Gridstone does, use VPC endpoints where it makes sense, like an ECR endpoint for pulling Docker containers, and then use the AWS ECR pull-through cache for public images from Docker Hub and biocontainers. Use S3 endpoints. This will ensure you get the highest throughput possible to AWS S3. EBS GP3 volumes are 20% cheaper than GP2 and has a more predictable throughput and I/O profile. Logs can get large quickly, especially on larger jobs. Ensure to set expiration on your CloudWatch log groups to clean up old logs. AWS Fargate may seem attractive and can further your serverless journey, but the fact really is it costs significantly more than EC2. One of the best ways to reduce costs is to use Spot instances. The best way to adopt Spot is to ensure your processes are doing the minimum amount of work to produce the results. You need to break down your long-running processes into smaller processes and fan them out. This ensures that when a Spot reclamation happens, and it will, lost compute time and costs are minimal. Once we do that, what's the best way to use it? Ensure that your batch environments are using all availability zones. This will ensure you have access to all available Spot pools, reducing the likelihood of reclamation of a Spot instance. Use multiple instance types and generations. So like the 4th, 5th, 6th generation C, M, and R instances. This will ensure the highest availability of Spot instances and further reduce the chance of Spot reclamation. Create a queue for jobs up to 16 CPUs and create a queue for 24 CPUs and above. Having this small and large strategy ensures that you don't have a pileup of small jobs on larger instances, and that larger instances are likely to get the exact instance type that they require, or larger jobs will get the exact instance type that they require. For some on-demand tips, my recommendation would be to use the latest generation instances. If you're going to pay full price, you might as well get the latest 6i generation of the C, M, and R instances, as they're faster and cheaper than the previous generations. So whether you're using Spot or on demand, you want to make sure you're making the most effective use of resources. As a first step towards right sizing, we want to either use Nextflow Tower or use the HTML report from Nextflow to right size your processes. Using these reports will show you the maximum, minimums, and averages on CPU, memory, disk space, and job duration, putting it all in an easy-to-read plot. This information will allow you to make informed decisions on how much CPU and memory to assign a process. Set the memory for a process to just slightly lower than what is intuitive. And when I say intuitive, I think like 4, 8, 16, 32 gigabytes of RAM, those nice numbers. But the reality is on AWS Batch, it's automatically going to leave room for the system resources. So let's say, for instance, you have a batch queue that maxes out at 16 CPUs and 64 gigs of RAM, and you submit 100 jobs that request 8 CPUs and 32 gigs of RAM. You'll wind up with 100 instances running at half capacity. This is because AWS is going to reserve that 1 to 2 gigabytes of RAM for the system. This is also the same for Slurm on pCluster. If you were to instead give it, say, 31 gigs of RAM, the result would be 50 instances at full capacity. Another important note is while you're right-sizing, don't starve your processes. Although it may sound counterintuitive when right-sizing, you do not want to hit 100% efficiency in any metric. The goal should be 75 to 85%. For example, in the image shown here, we had a single-threaded process that we were providing one CPU to, and we saw 100% usage. Because when we gave it two CPUs, it was reporting 52% usage. But when we dug in further, when it had two CPUs, the minimum runtime was actually 45% faster, and the maximum runtime reduced to 60%, negating the additional cost of an additional CPU and reducing runtime. Also keep in mind, these are averages over the lifetime of a process. It does not always represent the peaks used by a process. Once we've got a baseline on how to right-size processes, we can layer in automation. Make sure you use task attempts with your processes, even if you think you've right-sized it perfectly. By estimating the maximum memory, but then using more memory on task retry as a contingency, the contingency provides a higher likelihood of a retry succeeding. This avoids the pipeline failure and lost time. If the binaries in the process need memory defined like Java, use code to match. And to further express on this line or point is think of a pipeline that might fail at 1 o'clock in the morning and someone's not going to see it until 9 a.m. If you have that contingency, we can still have that pipeline complete for the person that's going to come in the morning, and then they'll see that there is a retry and they can research and look into why that had to retry. Next, dynamically assign resources to the process based on inputs when possible. When you're setting up a process, sometimes you can determine how much CPU and memory a tool is going to use based on certain inputs or parameters. For example, we were able to predict how much memory this particular process needs based on the input size. Lastly, provide validation checks. On runtime, you should be able to do some validation against parameters and inputs, allowing you to fail the job before it runs, saving time and compute costs. One of the things that I think everyone in our industry can agree on is that storage is and always has been a problem. So every instance uses EBS somewhere, and there's no built-in method to scale EBS. So that's where EBS autoscale comes in. EBS autoscale is going to allow you to choose a small initial EBS volume and then grow that logical volume by adding more volumes as space is consumed versus creating an EBS volume for the peak amount of space. By default, EBS autoscale will be liberal with the volume sizes as the logical volume grows. Keep this in check by setting the maximum volume size. We set the maximum to 150 gigabytes. EBS autoscale has the ability to create its own initial device, though I don't recommend this, as you can easily exhaust the EC2 API limits when scaling quickly. This can result in the EBS volumes getting created but not attached, and even worse, not deleted. This API limit can, hitting this API limit can still happen when a large amount of jobs are running. So set up monitoring of available EBS volumes so you can be alerted when there's orphaned EBS volumes. Moving on to S3. We often see that work directories are not cleaned up. By expiring data in the work directories using lifecycle policies, we can avoid this problem. When scaling quickly, jobs in the same batch environment can compete with the S3 maximum TPS, or transactions per second. So try to pre-partition your work directory buckets and auto-assign them on runtime. We do this through our dynamic infrastructure configuration. Use intelligent tiering, as this is helpful in the unpredictability of the scientists' data needs. Sometimes they need data now, and sometimes they want to recall all the data 6 months from now. So by using intelligent tiering, you're going to be able to tier down to the lowest costs while that data is not being requested. So to talk about storage gateway over data sync, this is a little bit of a side tangent. So lab equipment often needs to get results to S3. This helps you with automation and triggering different processes. Storage gateway offers the ability to stream that data to S3 instead of the bulk data transfers with data sync. What we have found is this results in less on-prem capital costs as well as lower bandwidth needs. Storage gateway also has multiple resiliency features that lend itself to automation with S3 events. Take, for instance, if you're transferring data up to the cloud and you have an interruption in your internet connection and then it resumes. The storage gateway is not a first in, first out type of device. So when the file gets there that triggers a process, all the data might not be there. So storage gateway has an API call that you can say, hey, let me know when everything in your cache is up to S3, and then I'll continue. Let me tell you about a recent experience we had with storage here at Gridstone. We had inputs grow that ballooned pipeline runtime exponentially. We found data transfers were long and I/O was heavy. We needed more I/O and identified instances with NVMe to help us do that. That'll be the D instances you'll see in the instance list. NVMe is significantly faster than EBS with multi-gigabyte speeds per NVMe and the ability to RAID multiple NVMEs together on larger instances. Scaling storage with compute, and the cost is similar to that of the same instance with the same amount of EBS. With all that speed, the bottleneck was transferring data to and from S3. With the AWS CLI with a single command, it maxes out at about 300 megabytes a second. We looked to Goofy's, though it removed the need to transfer ahead of time, its issues with synchronous reads and writes caused some tools like BCL to FastQ to fail. This is when we came across S5CMD. With S5CMD's ability to saturate a 40 gigabyte network connection and multiple NVMEs, we were able to greatly decrease transfer times between S3 and local storage. But how do we get this to work with Nextflow? Gridstone built a wrapper for the AWS CLI to direct S3 transfers to use S5CMD. This allowed S5CMD to work seamlessly with Nextflow. Here is a view from Tower on one of our pipelines. The only difference between the runs is the use of NVMe over EBS and S5CMD over the AWS CLI, meaning I made no changes to the pipeline or the configuration of the pipeline. The left shows the pipeline in its original state. This batch queue consists of 4th, 5th, and 6th generation CM&R instances up to 4x large. The right shows it running on NVMe instances using the S5CMD. This batch queue consists of 5D and 6ID CM&R instances up to 4x large. Using the NVMe and S5CMD resulted in a 13% reduction in runtime. But if we look closer, we also had a 21% reduction in CPU hours. According to Tower, we had a 59% reduction in estimated costs. Remember that Tower does not calculate EBS costs, so the EBS runs have a small but hidden cost, whereas NVMe runs more accurately reflect storage costs. Let's try to push this a bit further. When we enabled NVMe and S5CMD, we saw how much a difference it made without any pipeline changes. Then we wanted to see how it affected a previously right-sized process. Using the standard Illumina tool, BCL to FastQ, we had originally found 32 CPUs to be the balance between price and runtime of a NovaSeq S2 flow cell. Now with NVMe and S5CMD, we are finding 96 cores to be the balance regarding performance, cost, and spot availability. We tried it with 128 cores, but we got delays because of instance availability. There's only 3 instance types that have 128 CPUs, but there's 9 that have 96 CPUs. As you can see here, this switch made an equal impact on the S4 flow cell. Transfer time for the 3.2 terabytes, which includes sequencer data in and fast queues out, went from 4 hours and 18 minutes to 21 minutes. As a final mention, our largest pipeline, which creates 43 terabytes of intermediary data, was able to go from a runtime of 3 hours or 30 hours down to 12 hours after reprofiling all the processes in the pipeline. Now, we haven't given pCluster much love here. So let's talk about our pCluster storage journey, which started with EFS. EFS was great. It was fast, and it grew as we needed it to. But EFS's 30 cents a gigabyte got expensive fast. We enabled life cycling, but this resulted in EFS slowing down considerably due to infrequent access data not contributing to throughput credits. Recently, FSX released a multi-DRA support. We decided to move to FSX as it could act as a cache for multiple S3 buckets where we would keep home and ephemeral and data buckets, so we don't have to worry about active data to drive performance. FSX came with some additional benefits. It allowed us to leverage S3 lifecycling to reduce costs, being able to allow us to reduce down to as low as $4 a terabyte versus $25 a terabyte in EFS infrequent access. This also gave us a built-in backup solution using S3 previous versions, which we did not have in EFS, being that AWS backup costs more than twice the amount to store the data in EFS and infrequent access. The one drawback was that we had to manage an eviction process. AWS Labs actually had a starter script that we were able to tweak and make work for our purposes. Now, you can say you have to pay for S3 plus the overhead for FSX, but we were able to use FSX HDD12 with SSD caching to keep costs low. We also leverage Fuse drivers, a combination of S3FS and Goofies, that allows us to mount S3 in pCluster, so scientists do not have to download the data ahead of time. Instead, they can stream it on runtime. This avoids the need for duplicating data into shared storage, and that the data that is streamed and cached is deleted with the compute node. With all of that, I would like to drive home a few main points. Use Spot. This is the easiest and fastest way to dramatically reduce costs. Storage is typically the bottleneck, and CPU and memory have been abundant for over a decade. And improving storage typically leads to faster pipelines and reduced costs. With that, I would like to thank the Secura team for asking me to partake into today's panel and to continue supporting Gridstone's environments. With that, I'll go ahead and pass it over to Phil.
Cool. Thank you very much, Michael. That was a really nice talk, and I've got to say I learned a lot myself there and was listening very carefully. I think there's some really nice lessons to be learned, and some really nice kind of benchmarks and detailed tips there. So my name is Phil Yules. I work at Secura, but today I'm speaking with my NF Core hat on. I'm co-founder of the NF Core community, which is kind of a subset of the Nextflow community. And I'm going to talk a little bit about our experiences with cloud compute. I'm not as technically experienced as Michael with cloud, for sure. So my talk's going to be a little bit lower level, and it's going to be a bit more sort of focused on some of the recent things that we've been doing and what kind of my impressions and take-home messages would be for anyone approaching a cloud. So I'm going to basically come with 3 key points today, and some of that overlaps with some of the things that Michael had said in his talk, which is really good. We didn't see our slides really ahead of time, so it's a bit of a relief to see that we're kind of singing from the same hymn book, so to speak. So I'm going to talk about testing pipelines, making sure that stuff doesn't fail, basically. Talk a little bit about storage again and S3 buckets and things you can do to save money there, and then wrap up on also right-sizing and optimizing resource requests. So for me, one of the kind of most important things in my experience for running pipelines is just to make sure that they don't fail. It sounds simple, but the more testing that you can do when developing your pipeline, the better, really. Pipelines, when you're running on the cloud, if you run big data on a cloud and it goes wrong, it can get expensive pretty fast. So yeah, mistakes with big data, expensive. So my top tip would be, as you're developing pipelines and developing your analyses, try and set them up with small test data instead. Do all of your initial development work, all of your kind of setup work with small tests, so that if and when they do go wrong, it doesn't cost you a fortune. And then when you get to running the big data, you're confident that stuff is going to work. But of course, best still is if you can let someone else make all those mistakes for you, and you just come in at the end and use a nice, well-polished pipeline, which of course is where brings me on to NF Core. So if anyone in the audience is unfamiliar with this, NF Core is a community effort to build best practice analysis pipelines using Nextflow. It started off not with a focus on cloud computing or anything, just on collaboration on scientific pipelines, and it has grown well beyond my wildest dreams when I started this project off with Alex a few years ago. The main thing that people come to NF Core for is the pipelines. We have now 73 different analysis pipelines. We only have one pipeline per data type or analysis type, so this is 73 different types of data you can process with pipelines. And all of these pipelines just work basically with one command. Through Tower or running Nextflow, you can just do Nextflow run and the name of the pipeline, and it will basically work. So most common data types, we already have a pipeline to handle. What's a bit newer is we also have this component library which we're building within NF Core for the DSL2 language that Nextflow brought out. And so now every single process within the pipelines we build is shared as a standalone module, and different NF Core pipelines can install those modules and reuse them. And as of a few months ago, and the release of NF Core tools that came out last week, we also have sub-workflows, which are kind of chunks of modules, which you can also install into your pipeline. And these will be of particular interest to anyone building pipelines, but you know they can never be part of NF Core. Maybe you work in an environment where you need something proprietary, or you're building a very specific bespoke pipeline which will not be of general interest. You can go and look at this huge list of modules of different tools we support, and then with a few commands, NF Core modules install, you can grab these different modules, put them into your pipeline, and kind of build them like Lego block bricks, basically, just connecting the channels. This saves a lot of time, but also every single one of these modules and sub-workflows has its own set of tests, so you can be pretty confident that they don't have bugs within them, which saves you upfront time, but also saves you that kind of that later on time with testing. So these are kind of our version of unit tests. The NF Core community is really big now. We have approaching 4,500 people within our Slack, which is lots of support and help, and also a huge amount of experience. So pretty much whatever compute system you're working on, whichever cloud you're using, you can be pretty sure that someone else has already run these pipelines on an equivalent system. That's great news, because it means that if there's anything in that pipeline which might have system-specific bugs or problems, then they will hopefully have been ironed out before you get to that pipeline. Again, saving you time, saving you money. Something we've been doing for a year or two now is working with AWS, who have been very, very kind to support the project and give us credits for cloud computing, to do continuous integration testing on the cloud. So since the start of NF Core, we've used CI testing on initially Travis and then GitHub Actions to run very small test data sets that run the whole pipeline through in a few minutes. And we do that on pull requests, as you'd expect with most software projects. But we found there was quite a big gap between those running those small tests and then running the pipeline kind of for real with big major data sets, which are many gigabytes in input size, and also running these pipelines on the cloud rather than running them just on a simple instance, as happens with GitHub Actions. So what we did with these credits is we set up a system of automation where every time there's a pipeline release on GitHub, that automatically triggers a run. When we first set this up, it was before Tower could launch workflows, so we did this manually by submitting AWS batch jobs. Now this is all dispatched via our Tower account, which manages all the compute infrastructure for us. And so you can see the screenshot here. We had a release of the viral recon pipeline. This is a pipeline that does analysis for typically COVID sequencing data, but can work with any virus to do variant analysis and genome reconstruction. And so there's a new release of this pipeline, and we've kicked off 2 different data sets here with Illumina sequencing data and nanopore sequencing data. And these are real data sets which are open source, which we've taken from publications, and they have been kicked off and run on AWS batch infrastructure. This is fantastic because it means now we start picking up all of these edge cases which sometimes happen on cloud, and those can be fixed right away. And so again, you can have confidence these pipelines are going to work with realistic data in your environment. But still, you can directly go in and see the results which are generated by these tests. This is a screenshot of the NF Core website now. And if you go to any NF Core pipeline, go onto the pipeline page and click the AWS results tab, you can see this file browser embedded within the browser, showing you the results from the pipeline version that you're currently looking at. And you can click through, see which files are generated, which is useful to get a feel for the pipeline. And you can also access, these are public data buckets. So you can access this data yourself, download it, and use it for benchmarking or comparison to be really confident in what the pipeline's producing. And you can even go through and interactively view all the HTML reports and things within the web browser. So we're looking at the multi-QC report here from that viral recon release. So, and what's new in this story is that we've been doing this with AWS for a couple of years now. And as of a couple of months ago, we're very happy to have support from Microsoft as well. So very soon, within the near future, we're going to be running these release tests, both on AWS and on Microsoft Azure. Maybe one day we'll also get Google. So whichever cloud you're running on, we will have automated full-size tests set up and running. OK. That's my big pitch on NF Core and why you should come and join us and use our pipelines and hopefully save money on the cloud. I'm going to talk a little bit now about kind of some of the work we've been doing actually just in the last few weeks with these automated megatests, as we call them, on AWS. And we've gone in and sort of done a bit of digging around and seeing if we can optimize the cloud compute costs that we have with our credits on these tests. There's a couple of things that I think were really salient learning points for us. The first one I've entitled Know Thy Buckets, which I was quite pleased with this section title. So here I've got a couple of tips about storage and specifically in S3 buckets. Typically, a Nextflow pipeline has 3 types of data. You have your input data, so these would be your FastQ files or your mass spec data or, I don't know, whatever type of input data you have, which you need to have somewhere in a bucket ready for your pipeline to access. You have your work directories. These are the intermediate files created by Nextflow as it runs through the pipeline. So every single process, every single task has its own work directory with all those files staged in and all those intermediate files. And then finally, you have your results, which are the finished product from the pipeline, stored by the published directive within the Nextflow pipeline. All 3 of these data types have different sets of requirements, and there's different things you can do to optimize the way that they work. One of the things that is worth thinking about with input data is that the way that data is transferred through onto your instance. Michael covered this already in better detail than I'm capable of, but make sure that you are using the right type of network connectivity between your instances and your S3 buckets to make sure you don't get charged for this data transfer. The work directories themselves, once the pipeline's finished, if everything went well and you don't need to resume that pipeline again, you probably don't need those intermediate files. They can be safely deleted if you're confident in your results. And so what we use is lifecycle rules on the S3 buckets, by which I mean we have all the work directories in a single location within a bucket, and then the lifecycle rule tells AWS if a file has been sat in here for more than, I think we have it set to 10 days, delete it. So that is constantly being cleaned out without us having to do anything, and that keeps that work directory as small as possible. And this makes a massive difference because that work directory can get very, very big very, very easily. But by waiting 10 days, it means if a pipeline fails, we can still resume it. Finally, the results directory, again, Michael touched on this. Intelligent tiering saves the day. Here, when you dump your results into a bucket, you may or may not need to be able to access them very, very quickly. And by setting that bucket policy to intelligent tiering, AWS will be able to scale down the storage class to whatever is most appropriate and cheapest for you. And this can, again, save a lot of money. So this is a plot from our AWS console a few days ago where we went in and did a bit of clearing up. And this really illustrates a couple of things. You can see us switching a bunch of stuff over to intelligent tiering. You can also see that the footprint of the storage dropped massively. We managed to clear up about 50% of our files. I had a terminal window sat on my screen over here, which was just had a scrolling delete log for several hours one morning. And so really this comes back to the title of this section, which is know what your data is and know where it is. We're quite lucky with the automated tests because we set up a file structure based on the commit hashes of the releases, everything structured in a fairly logical way. And so I could quite easily write a Python script that spidered all of the files within our S3 directory and checked whether those commit hashes actually did correspond to a known release. And by doing that, I found a whole bunch of release files, of test files, which were not associated with any known release, which could be deleted. I also stumbled across a bunch of work directories held in the wrong place, and various other kind of weirdness and input data which were no longer needed. And so we were able to delete a massive quantity of data and save ourselves a ton of money here. So by having well-organized data, really splitting up these 3 different use cases and thinking about how you use S3, you can save a lot of money and you can use your compute credits or your compute costs in a much more efficient manner. Right, final section from me then. Again, Michael has done a really good detailed description of this, and mine's going to be a bit more high level, but basically the same thing about right-sizing your resources or optimizing and streamlining your pipeline configs. Now, basically, especially with NF core pipelines, something you need to remember is that we build pipelines for everyone's data. Our priority when we set up these configs is that pipelines should run for most people most of the time. And especially with some of the bigger pipelines like RNA-seq and many of these other ones, people run on a phenomenal variety of species, of different data types, different data sizes. And so we try and be a bit generous with the default config so that people don't come back the whole time saying, oh, my pipeline keeps failing because it's not assigning enough memory. So you can probably go quite a long way by taking our off-the-shelf pipelines and streamlining the configs so that they fit your specific data and your specific use case. Here's that screenshot again from the Nextflow report, or you can view it within Tower if you're using Tower. And there's different tabs. There's usage, but there's also percent requested used, both for CPUs and memory. And so this is from the methyl-seq pipeline, I believe, where I was working with it a few days ago. And you can see that none of the tasks within this, none of the processes within this pipeline are really going beyond 50% of their allocated memory. In fact, many are way below that. And that's to be expected because, like I say, the default config is pretty generous. So you can go in and you can look at these plots and these metrics and try and work out what is a sensible number for you. And the beauty of Nextflow really is that the pipeline code and logic is separate from the configuration files. And so with any Nextflow pipeline, including the NF core ones, you can build your custom config files and you can overwrite all those defaults very, very easily and have quite complex and kind of elegant syntax for doing that. And so a minimal example here is a config file which says, looking for a process with this specific name, I want to allocate it 100 gigs of memory. Now, you can imagine that you can start building these config files out and you can be more or less specific. We have labels which have consistent naming within NF core, so you can bulk change the request for a whole load of processes in one go, or you can really kind of drill down and start doing it per process, which is more time consuming for you, but allows a greater level of fine-tuning. Because doing this manually is quite a laborious task and quite difficult, and if you go too far, stuff goes slow and starts failing, and there might be tens or even hundreds of different processes within a single pipeline, and you may be running very many pipelines. Realistically, I think many people don't do this because it's just not really a feasible amount of work. So one of the features which I'm really personally excited about within Nextflow Tower is the ability to do this automatically. And this is something that's come out relatively quietly, very recently. It's on a cloud instance of Tower. And now when you run a pipeline and it finishes, you'll see a subtle little button which has appeared saying optimization available. Now, if you spot that and you click on it, you'll see it brings up a little modal window. And what it does is it looks at how this pipeline ran, and it looks at what it actually used, and it will build you a config file which is tailored specifically for that run for that pipeline. And you can see here, this scrolls down for a long, long, long way. And there's a specification for every single process with the CPUs and memory that is appropriate for how it ran. And this is an optimized config, and you can take this and you can rerun the same pipeline again using this config, and hopefully that will be much more efficient. And this is fully automated, so you can do it all within a few clicks. There's a lot more in the pipeline for this, so to speak. So sort of stay tuned on this feature. There's more advanced features coming, and I'm really excited to see how this progresses. And I'm also hoping, selfishly, that we can start to make use of this within the NF Core community, so that the pipelines we build and ship come with even more better refined configurations, which still work for most people, but are hopefully a little bit more efficient. Right, I'm going to wrap up on my stories now. My kind of final point really is just to point you in the direction of some other really, really good resources. In October, we had the Nextflow Summit 2022, which is kind of a conference for NF Core. It's the first meeting we've had for several years due to COVID, and it was a lot of fun, and it was really successful from my point of view anyway. And I'd specifically like to point out 3 talks that we had. Angel from AWS, Venkat from Microsoft Azure, and Hutton from Google Cloud. All 3 of them gave really excellent technical, detailed talks, very tailored on using Nextflow specifically within their respective clouds and how to optimize costs. And I really recommend going and watching, doesn't matter which cloud you're using, go and watch all of these talks, because they all had points which were applicable across the different cloud providers. Really excellent talks. And you can do that by going to the summit, summit.nextflow.io, and you can find every talk that happened at the conference. It was live streamed on YouTube, and all the YouTube videos are embedded there, so you can go through and watch at your leisure. With that, thank you for your time. Please do come and join NF Core. There's a link there at the bottom for the NF Core website, but you can Google it easily enough. Jump onto our Slack, say hello, ask any questions, and we'll be happy to try and get you started. And if you're new to the world of Nextflow and NF Core, we have a free online training coming up in March, which you're very welcome to join, and a hackathon soon after that, which are a lot of fun. So hopefully we'll see you around, if not already. And with that, I'll happily take any questions along with Michael. Thank you.
Yeah, thank you very much to both Phil and Michael for these really nice presentations. So just as a quick reminder, if you have a question, please type it into the Q&A box. And we would also like to ask our attendees to take a moment after the webinar has ended to take our exit survey and give us your feedback. So with that, let's see what we have for questions. Yeah, we have a bunch of questions for Michael concerning his part of the presentation. So one of them is, did the Nextflow jobs automatically use the NVMe volumes instead of the EBS, or did you have to configure something yourself? This is for Michael.
So to answer that question, no. So okay. What we do is we have 2 different launch templates, one with EBS, one without, and then we have scripts that can identify if the NVMe is available, and if so, formats it, raids it, and then makes it available to the EBS autoscaler to use as its initial device.
Okay, thank you. Question for Phil. Is there any reason that you focus mostly on AWS and not GCP?
Yeah, very simple one. AWS gave us credits.
Right, yeah, you mentioned that. Mm-hmm.
So yeah, we had that available to play with for a while. Like I said, Microsoft have started supporting us just recently, so we're we don't have that set up. We're in the midst of playing with Azure and setting up infrastructure at the moment. And we have had some conversations with people working at Google, so I'm hopeful that maybe we can get something set up with them in the near future as well. But
okay.
Just watch the space for now.
Great, thank you. Another one for Michael. Is your S5 CMD wrapper open source?
It's not available yet, but I am working on a generic version to share with everybody.
Okay, any timeline for that? Or?
It's the holidays, so maybe early next year.
Yeah. Okay, all right. Other one for Phil. Is there a framework or tool for trying a range of values for resources to allocate to each process, with the goal being to efficiently optimize these resources?
Yeah, not that I know of. I've had some conversations like this in the past because it feels like this would be a really nice thing to do, to say, like Michael said so elegantly, it's not always just a question of bringing down the values and to whatever is cheapest, because that can affect runtime and stuff. So casting a wide net and trying out lots of different stuff could be a good way to go to try and optimize the cloud costs. And of course, this would lend itself very well to like a machine learning approach or something like that. So there's loads of scope for improving this more in the future and automating it. I don't know of any way to do that right now, but again, if you've got any ideas and you'd like to get involved, please tell us, because I'd like to hear them. And otherwise, I'm pretty confident we'll start seeing more things like this coming out soon.
Okay. Other one for you, Phil. Generally speaking, what do you think are the best features of Nextflow Tower for NF Core, your tests, and your cloud usage?
So I'm fairly happy to say this because like I say, we originally set all of our infrastructure up without Tower because at the time we used Tower for monitoring runs, but it couldn't launch them for us. And I can tell you, writing those GitHub action scripts and setting up all that AWS infrastructure took a long time, and we got it wrong a lot. And then we switched to Tower, and it's been just much easier. And now we're setting up Azure. Once we get a few of the key pieces in the back end for Azure, we'll be able to just give a different compute identifier when we launch the job, and otherwise everything's going to be exactly the same. As part of the process of setting up that automated testing, I should mention, I actually wrote a GitHub action, which is available in the GitHub Actions marketplace. I think it's called NF Core Tower or something like obvious, Tower Action maybe. And so you can drop that into your GitHub Actions YAML file, and just with a couple of lines, it uses the Tower CLI command line interface. And you just put in your parameters and your compute identifier and things like this, and your API key with a GitHub Action secret, and it just launches everything for you. So it's super easy to run via Tower now, using GitHub Actions.
And we just got another Tower-related question. Will optimized resource limits be automatically deployed in Tower in the future on rerun of the associated individual runs?
So it's automatically available if you're using the managed Tower cloud, the cloud.tower.nf version right now. So any new pipeline you run, as long as it's finished successfully, I think that should appear, and you should have that option. Hopefully that answers your question. In terms of automatically optimizing resources without you clicking that button and without you transferring a config, that doesn't happen yet. You still need to do it manually. I think it's a bit risky to do it without really kind of asking the user. But I'm hoping it's still a bit manual. It generates the figures for you. You need to transfer the config. And I think the UI and the interface and everything is certainly going to get a lot easier in the near future.
Okay.
That answers your question.
Great, thank you. Question for Michael. Do you only enable NVMe for IO-heavy workflows, or is it worth enabling them across the board?
We have it enabled it across the board in certain environments and have in others, and I would recommend it just making it your default queue.
Okay. All right. Other question for Phil. Somebody says they have generally used the Nextflow biotech blueprint to run Nextflow pipelines on AWS. Would you suggest a different way of doing things?
There are so many ways to do this. So, I mean, I think it's going to be difficult to avoid that annoying answer of it depends. I don't know that blueprint. I haven't used that myself. It depends on, like Michael, for example, you're doing a pretty well-defined workflow with very high throughputs, where you're doing a lot of stuff on the cloud. So that kind of setup, I think it makes sense to really drill down and have high levels of kind of control over every aspect. We run much less. We run a massive variety of different data sets, so it's harder for us to do that. And there's, according to the type of data you're running, the type of pipelines, the frequency, the volume, how many resources you have to actually control stuff on the cloud, all of these variables will affect the best way to set up infrastructure on AWS. But the thing that I've mostly used myself, we've used it here, and when people have a lot of problems, I usually recommend it. Within Nextflow Tower, there's a feature called Tower Forge, where basically you set up, I think, just basically permissions within AWS. You need to set up an IAM user and a couple of other things. And then there's kind of a button that you press, and that will set up all the batch queues and all that kind of stuff for you within Tower, within AWS. And that, for my personal experience, has been by far the easiest way to set up AWS infrastructure, because generally clicking that button stuff just works. And whenever I've tried to do it myself, it's taken me a long time and a lot of errors.
Yeah, okay, great. One participant had a question for Phil. He or she says they checked some of their pipelines and can't find the optimized configuration. Maybe you want to go back to that slide and point out again where that can be found?
Yeah, exactly. So the optimized configuration is not part of NF Core. This is available within Nextflow Tower. So if you go into, if you're using Tower yourself on a cloud instance, this is very new. It's not been around for very long. If you go into cloud.tower.nf and you run your own Nextflow pipeline there, and hopefully you'll see this text here on the run page saying optimization available, and clicking that will give you this optimized config. This is not yet something that we so we have this, obviously, we're doing all of these ones in our NF Core space on Nextflow Tower. But it's not yet something we've been able to bring back onto like the public NF Core website yet. It's only been around about a month, so we need a bit more time to be able to do that. But there's definitely my hope to try and make this information kind of publicly available, so it's useful for everybody.
Great. Yeah, let's see what else we have. Michael, why do you use manual batch environments instead of Tower Forge?
As Phil said, Tower Forge is great. I've tried it, I've used it, and it's very simple. It probably takes 10, 15 minutes and you can start running pipelines. What we have found is that Tower Forge is limiting for us and our higher scalability needs. We're able to get into much more of the weeds when we manage our own environments.
Okay. Yeah, makes sense. Why do you create infrastructure configurations on runtime?
So we're able to provide all of the pieces of the environment that a pipeline will run in, right? So we have like our R&D environment, our production environment, our validated environment. All of those have different batch queues. And in your configuration, you need to put in like the ARN of a batch queue. So what we're able to do with our dynamic launcher is on runtime, we pull all the pieces of the environment, and then we automatically configure like email. People want to be able to send emails directly from Nextflow. We put in the SMTP server, the username, the password. People don't want to have to put in the Docker registry, so we automatically put the Docker registry in so they don't have to change their pipeline. The name of their container is the same throughout all the environments, and we just change the registry. And the biggest one is going to be different characteristics. We talked a lot about MVME, so we just have a Nextflow label that you put on your process that says MVME spot, and it'll go to a batch queue that is running MVMEs on spot instances. And we do that for different GPUs, the small, large queues we were talking about, and probably a couple other things that aren't coming to my mind at the moment.
Okay, great, thank you. Other question that just came in from Michael. Do you have CloudFormation/Terraform templates for your AWS infrastructure? And is there any chance you might be able to make those open source?
We do. Every single piece is is in CloudFormation, from networking to the batch environment to the Nextflow pieces. I'm not sure if we can make that open source at this time.
Okay, great, thank you. Question for Phil: have you ever had any expensive mistakes?
Yeah, I think you ask anyone who's been running stuff on the cloud long enough, probably people have some scare stories.
What's your scare story?
I've been pretty lucky, I think. We haven't had anything massive. We've had a few blips. I think right when we were starting off, I was a little bit eager in setting up some of our infrastructure, and I had to set up with my personal credit card. And so the first few runs came onto my personal credit card before the credits had been activated. That was probably one of the worst. That was a bit of a nasty spot, but nothing too terrible.
Nothing too terrible. Okay, that's good to hear. And generally speaking, your experience is running on the cloud cheaper than running with local compute sources?
It's another it depends question. This is, again, very much dependent on the types of workflows, but also the how predictable the flow of your data is. So if you're working in a place where you have the same number of sequencing runs coming through every week, and you know there's going to be roughly this many terabytes of this kind of data, then that's much easier to handle on kind of on-prem cluster system that you have. If you're working in a more bursty environment, then that's typically a good selling point for using cloud, because with cloud, you only pay for what you use. So you can kind of scale infinitely, and then when you have no data to analyze, you can scale it right back again. So there's things like that which can define whether, and depending on your workflow, cloud could be cheaper or it could be more expensive. Also the types of infrastructure you need. And of course, the other thing is how long you've been running and how much data you have. Cloud is very good to get up and running quickly. So if you're kind of starting out, you can be up and running like Michael said in minutes or hours, without having to kind of really make very long predictions about what your usage is going to be for the next X years to procure all this infrastructure. And it also means if you're not sure about quite how fast you're going to scale and stuff, then that you do it. So, I mean, if you're very, very good at making guesses, and if your workflow is very predictable, then on-prem might be cheaper. But otherwise, cloud could be cheaper. So it depends. Okay,
got it. Yeah. Couple of questions from Michael. What has your experience been with spot reclamation, and also your experience with EBS autoscale?
Oh, that's a whole lot in one question. So spot instances, it really depends. We've noticed different types a year. We used to be able to run our GPU workloads on spot with no problem, and then about a year ago, we couldn't get a spot instance for weeks. We actually had to switch our GPU over to on-demand while we try to explore the more proprietary GPU instance types. What was the other part of the question?
The other part was about your experience with EBS autoscale.
My experience with EBS autoscale has been good. I've actually made a few contributions to the public repo. It is in the AWS Labs repositories. You can actually find the NVMe script in part of those. If you dig into the issues, you can find them there. But it's been relatively good. People do respond on the repo. My only issue is just a couple of times we've had like terabytes of abandoned EBS volumes.
Okay. Okay, great. Yeah. One last question I want to squeeze in. It's not directed at either of you, so maybe whoever wants to answer that. Is it possible in Nextflow to report the maximum resources used for a given process instead of the average?
Yep. So in that report, you've got the box plots, and the box plot shows maximum, minimum, and median. So if you look at the top whisker of all those box plots, that should be showing you the maximum for that any task from that given process. And if you look into the trace files, you have all that more detailed information as well. Yeah, exactly this one. I was also just listening to you talk about spot instances and thinking as a fairly new Nextflow feature, which is maybe worth knowing about. Michael showed that when jobs fail, you can set them up to automatically retry with more resources. But spot instances, if your spot instance is killed, you probably don't want more resources. You just want it to try again. And so now Nextflow handles spots cancellations differently to failed processes, and it will not count as a retry. It will just resubmit that job with the same resources again whenever it can.
Okay.
Just kind of a nice feature.
And I can confirm that that works pretty well.
Yeah, okay, good. Great, yeah, that's actually all the time we have for questions today. So let me thank our speakers, Michael Kroll and Phil Yule, and our sponsor, Secure Labs. And if we didn't have time to get to your question, we will try to have someone follow up with you via email. As a reminder, please look out for the survey after you log out to provide us with your feedback. And if you missed any part of this webinar or you would like to listen to it again, a link to an archived on-demand version will be emailed to you, to all attendees. So with that, thank you very much for attending this Genome webinar.